looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Azuzin. Let's make a little bit of announcement as usual and officially start the stream. I hope anybody watches me, right? Somebody at least, right? Because we're streaming at very unusual time because my sleeping schedule is fucked up again, so it is what it is, and it isn't what it is. And so, Red Circle live on Twitch. And what are we doing today on Twitch? A television website, my favorite website of all time. Today we are programming in Rust. But you didn't expect that shit to happen. Right, I'm gonna give the link to twitch.tv/searching, the place where we programming in Rust, and I'm gonna ping everyone who's interested in being pinged. Right, there we go. The stream has officially started. Hello everyone. Welcome, welcome, welcome. So today we're gonna continue developing Nock. Do you guys know what the fuck is Nock? Nock is not a cock. So that's very important property of Nock. It is not a cock. Why am I actually using cock as a countable noun? It's a name of a language. It's not cock, right? So I'm going to give the link to Twitch chat, and also I'm going to put it in the description for people who potentially watch that on YouTube. And what is a Nock? What is Nock? It's an expression transformer, right? It's a symbolic expression transformer, specifically designed for recreational math, right? Playing with recreational math and stuff like that. In some regard, it may remind you cock, but it's not a proof assistant. It's not cock. That's why it is called Nock. Right, so let's take a look at it. All right, so I'm gonna go to here. So this is Nock. Wait, why did I do it like that? There we go. So, and yeah, it is written in Rust, right? So I already mentioned that. We can start this entire thing. There we go. So this is REPL of Nock. This is REPL of Nock. So essentially what it allows you to do, it allows you to so-called shaping of expressions, right? So essentially, you can start shaping a particular expression, and for instance you want to like swap around some arguments and stuff like that, and you can say, okay, so I'm gonna say a plus b equal b plus a, and I'm gonna apply that to all matches of that pattern, and as you can see I just swapped things around. Right, so it basically allows you to specify expressions, then specify patterns of those expressions, and specify how you want to transform all of that stuff, right? So that's basically what it is. It's not really a proof assistant, though you can use it to prove things, to prove statements, but this thing is not going to assist you in that. If you make a mistake, it's probably not going to tell you that, right? It's probably not going to tell you that. In fact, we looked in depth into how to prove things in Nock in a previous stream, right? So I wish I could actually give you the link, but I mean, I could go to YouTube, but since I'm streaming, it's going to take some time, but the link is going to be in the description, right? So link to previous stream, right? So, and we considered all sorts of things, right? And specifically we considered how to do mathematical induction in Nock. And you know what's funny, chat? You know what's funny is that on that stream, when I was doing and exploring mathematical induction in Nock, I made a severe mistake that I only noticed when I watched back the VOD, right? So for those who doesn't know, I actually watch all of my streams back, the ones that I plan to actually post on YouTube. I actually watch them back from the beginning to the end very carefully. And I also cut out all of the dead air, like breaks and stuff like that. And maybe when I was stalling for too long, I just like make it more watchable and everything. And I caught the problem during the rewatch. So the problem that I caught is that I was not using mathematical induction correctly. Wasn't using it correctly, like at all. And this is because Nock doesn't really check anything, right? So it's not assisting you because it's not a proof assistant, right? Doing the actual proof is completely on you. The only thing that Nock provides you is an ability to transform expressions. I may actually reproduce the kind of problem that I encountered, right? So let's actually go ahead and define maybe addition on piano numbers, right? So for those who doesn't know what is piano numbers, you may want to probably look at the piano axioms on Wikipedia, right? I'm going to paste it in here. So somebody asks, what was the mistake? I'm about to explain that. I'm about to explain that. Don't worry about that. Right, so this is going to be that. So TBD. So let's actually define the addition on piano numbers. So usually it consists with a base state, right? So it's a sum ID, and right, 0 plus a is equal to a. So this is the base state of the sum addition. So then we want to define a sum state, a step, right? So we're going to pattern match the first argument like so, and we're going to say that this is going to be equal to a plus b. That way, we're essentially define an addition, right? So if we have two numbers like s of 0 plus s of 0, right, and you try to shape it, you can apply the sum rule a couple of times, and then as you can see, you would get a thing that matches the sum ID rule, like so, and there you go, you just added two things together. So you had 2 and 1, and the result was 3. Which is correct, right? So this is basically the definition of sum on piano numbers, and we mechanically just demonstrated how this entire thing works, right? So this is actually a pretty good demonstration of how NOC generally works. So one of the things I want you to do, I want you to prove another statement on this thing. I want you to prove that sum ID is also commutative, right? So it is actually enough to define this thing for this thing to be commutative, right? So something like this, a plus 0 is going to be a, right? So these two things, just a second, these two things are axiomatic, but this one can be actually proven through these two things. It can be actually proven through these two things. So, and let's actually go ahead and do that. So I usually do that through induction, right? So let's define an induction base, right? So the induction base, we're going to be inducting by variable a, because that's the only variable we have in here. We don't have any other variables to induct by. So this is going to be 0, and this is the statements that we want to actually prove to be true. So it's a very easy statement to prove. It's just sum ID. And there we go. So we have 0 equal to 0. So we need to define reflexivity to actually say that this entire thing is true. Let's say that if a is equal to a, this is a true statement, which allows us to just do something like that. And there we go. We just proved that the base of the induction is actually true. Right, so the base of that induction is actually true. So the next thing we need to do, we need to define an inductive step. And this is where the shit hits the fan. This is where it becomes kind of difficult. Look, so the inductive step is essentially S of A, right? So it's S of A, and that's the statement that we want to prove to be true. And while proving that statement, we can kind of assume that the previous step is correct. That the previous step is correct. And the way we do that is that we just apply sum, and as you can see, we got to the point where we have the sort of like an inductive hypothesis in here, so we can apply this inductive hypothesis, and we effectively just proved everything, right? But there is a little bit of a problem with the inductive hypothesis, basically the statement from the previous step. The problem is that the variable by which we are inducting can match not only this, right? So this entire pattern matches not only this, it also matches this, right? It also matches this. Let's actually go back, right, to the beginning, to the very beginning. So this is what we had initially. So what I can do is essentially just take this inductive hypothesis and already apply it, even though this is completely illegal. It is completely illegal to do so, but I still can technically do that because A is a variable and it matches this thing. You see what I'm talking about? You see what I'm talking about? This is very dangerous, and this is why I said that NOC is not a proof assistant, because you can make mistakes like that, and NOC is not going to correct you or anything like that. It's just a dumb pattern matcher, dumb expression transformer. It is very subtle. It is extremely subtle, but this is something that you can do. Luckily, when I posted that video, somebody in the comments, I forgot their name, something like Phoenix or something, please remind me if you're watching right now, please say something in the chat. They suggested an ingenious idea to solve this problem. They suggested an ingenious idea. They suggested what they essentially did. Right, so they suggested to not use this thing directly. To not use this thing directly. So let's actually delete this thing. Just simply define some id com hypothesis, which is that, but instead of variable, use a symbol. Specifically for the mathematical induction, use a symbol instead of variable. And symbol cannot match anything but itself. It acts like a number. It acts like a number. So if you define this hypothesis, right, so you have a base, you have a hypothesis, the next thing you have to do, you have to define an inductive step, right? And within the inductive step, you can only use this hypothesis, but not the original statement that you're trying to prove. And again, you obviously have to use the symbols in here, right? So this is going to be the symbols, and this is what you wanna prove. So something, oh yeah, this has to be equals. Right, so let's actually take a look. And because of that, you simply can't use, well, you can use this thing, but you're just like not allowed. You just can't use this hypothesis until you actually shuffle things around enough when it's applicable. You see? So basically, within the inductive step, you should never use the statement that you're trying to prove. You have to have this additional hypothesis that uses symbol instead of a variable, which makes it only applicable when it matches exactly. And it's actually a little bit more, let's say, type safe, so to speak. It's a little bit more type safe. Does it make sense? So in that case, the inductive proof for this statement consists of these three statements, right? And they're a little bit more type safe. They are a little bit more type safe. And I think I want to actually go through the standard library, right? And I actually put all of the proofs that we did on the previous stream into the standard library. I want to go through the standard library and actually change all of the inductive proofs to be like that. But obviously, I'm not going to do that on the stream because it's going to take some time. But yeah, this is such a cool idea. Thank you so much, whoever suggested that in the comments, because yeah, that solves the problem. That actually solves the problem. Right. So it's just a reminder again that NOC is not COC. It is not proof assistant. It just transforms the expression, and that's kind of the whole point. So do not rely on it too much. Be very much skeptical of the results, right? So it's just here for you to mechanically transform things, right? Just mechanically transform things. All right, so what I want to do today I want to extend NOC a little bit and add support for a feature that I really needed while I was proving rather complex things. Right, so imagine that you have a property of some commutativity, right? So for example, a plus b equal b plus a, right? And you're working with a pretty sophisticated expression, so something like a plus b, c plus, something like that, multiplied by d, and this one, right, this one is something like plus 5, and so on and so forth. So you have expression that looks like this, and then you want to actually swap around the inner expression in here, right? So the way you do that in NOC, you can actually specify the rule that you want to apply, the sum commutativity, and you can specify the index of the sub-expression on which you want to apply that thing, right? So I want to apply it to one. No, this is not the one, right? I want it a plus 5. Is it something like 0? No, it is not 0, right? So it's something like 2. Yeah, this is 2. You see, it's very much inconvenient. It is very much inconvenient because, like, we don't really know how exactly it enumerates them. Well, I know how it enumerates them. It actually does DFS, depth first search, on the AST, and it enumerates them as it encounters them, right, in a DFS order, right? And that's the index you're supposed to use in here. And it is very useful when you want to have like a very fine control right? You want to have a very fine control on what expressions you want to apply, this kind of stuff. But then, like, if you have a very sophisticated expression, it's not clear like what index you have to use. Sometimes, like when I work with very big expressions, I have to use like a index 10, right? And it would be nice if I had something that would show me that like this number, this index is associated with this sub-expression and stuff like that. Right, so what I came up with, right, so theoretically, is some sort of like a match command, where I provide the rule, right, where I provide the rule, and it would basically find all of the matches for that rule and just show me, display all of the like sub-expressions that match all of that and highlight them and show me the index, so I can pick that index and use that index within within the tactic, within the transformation and stuff like that. So this is basically what I want you to implement. This is basically what I want you to implement. Sounds good? Sounds Gucci? Sounds Atamaguchi? Let's go. Right, so that's the plan for today. So I also have a couple of more to do to implement, but I think that's the primary one, right? So that's the primary one. So I'm gonna go to Noken here, and let me go to the commands, right? So we probably need to introduce a new command, right? So I think I have what to do, yeah, match command that shows all the matches for pattern rule and enumerates them with the indices that can be used in the strategies. Right, so that's basically what we are doing in here. So let's find the enumeration command. Right, so how we're going to call this? This is going to be a match, and match is going to probably accept a name, right, of the rule that we're applying, right? So it's going to accept the name. So let's actually try to compile this entire thing and go to the compilation errors, right? So because we have a huge switch case, and the question is how we exactly, implementing all of that. So this is basically the name. So the rule name, and the first thing we probably want to do, we want to find the rule by its name, right? So as far as I know, we have a context, and within the context we have a list of all of the rule definitions, right? So it's basically a vector of pairs which associates token with a specific rule definition. So the reason why we're using a vector is because I need to preserve the order of the definition, right? We need to preserve the order of the definition. I want them to be in the order as I'm defining them, because I'm listing them in that order and I'm saving that in that order. And the easiest thing to do was at the time is to just use a vector, right? So obviously searching within that thing in linear time is pretty slow, but we're not really working with too many expressions yet. So once we have enough expressions for this thing to become slow, I will think about some better solution, right? So maybe I'm gonna keep the order of the definition within the rule definition, and when I'm displaying that, I'm just basically sorting by that, right? So that way it's a little bit faster. But right now it's not a problem, but I'm keeping that at the back of my head. So alrighty, so what I want to do get item by key. So I have a special helper that allows me to just quickly find right, these things. So this is going to be rules by a particular name, and we either get something from this entire thing or don't. Right, so this is going to be a rule definition. Maybe I'm going to call it rule def. All right, so this is a rule def. And this thing actually returns, if I remember correctly, it returns the pair. It doesn't return just the value, right? So if we take a look, it returns option key value, right? So it's option key value, but I don't really need the key. So I think I'm going to just go ahead and map, not mappe, but rather map. Right, so this is going to be, so I don't care about the key, I only care about the value. So I'm going to just extract the specific value, and this thing is not implemented yet. So in case of we cannot find the rule, we have to say something to the user, something like diag report, and what we can say in here. So we have to report at the location of the name that we provided, and the severity of the diagnostic is going to be an error, right? So we can say something. Rule name does. Can you see shed, by the way? Right, I just realized my camera is actually too big. Right, my camera is too big. Okay. Fuck, I'm really sorry. Right, I remember that I changed my camera to be like a little bit bigger for the video purposes, and yeah, so I need to also put something behind my camera. I really apologize for that. I hope you didn't, you know, didn't miss too much of the explanations. Yikes, 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 yikes. So rule name does not exist. A rule name does not exist, and I'm gonna just do name text. And after that, I suppose we have to return like none and everything. Okay, pretty cool. So we have a rule definition, and within the rule definition, what do we have? A rule definition. So definition. So we have a rule, right? Rule definition. And within the rule, if I'm not mistaken, if we go somewhere here, struct rule. It's not really a struct, it's actually something like this. Yeah. So we have two kinds of rules. There is a user rule, which is basically, you know, head and body, and body is essentially head equal body. And an example of such rule is a plus b equal b plus a, right? So this kind of thing is called rule, and the left-hand side of the rule is called head, and the right-hand side is called body. It's kind of an old terminology, but I just kind of like settled with it, so yeah, it is what it is. And this is specifically a user rule. We also have a replace rule, which is a built-in rule. It doesn't have a head and it doesn't have a body. It's a special magical rule, which I'm probably not going to cover on today's stream because it's very subtle, right? So, but with this kind of rule, you can kind of emulate like an actual lambda calculus, right? But it's not really, you know, finalized yet. I still haven't decided how exactly I'm gonna, you know, go about it. So I'm not gonna really go too much into this kind of thing. But we need to keep in mind that there is such special rule, and it doesn't have a head and it doesn't have a body, which means that if I try to do something like match replace, I should probably throw an error. But not necessarily, because replace actually does have a head. Replace actually does have a head, but it's hard-coded. It's not visible. It's not visible like at this particular level. I think it's hard-coded somewhere. Let me find. So there was something about replace specifically. I think it's somewhere here. So here is the replace. Yeah, there you go. That's basically the thing. All right, so that's the rule that we have in here. All right, and I would like to maybe, I could have just copy-pasted it in there and just like make the following thing that, right, so we have a rule definition. Within the rule definition, we have a rule, and we can just pattern match this entire thing like so, right, and say that rule user head and body, we do one thing in here, and in case of replace, we do another thing in here, a completely separate thing. But overall, it's going to be basically the same. Furthermore, we're going to be matching by the head. We're going to be matching specifically head, which means that maybe what we can do, we can simply return head in here. We can, of course, ignore the body, right? So, and here we can simply hard code the pattern that we got in here. So we can simply hard code it like so. So that's the pattern, right? And then say, okay, this is the head. Not a bad idea, right? So essentially, yeah, it's sort of a little bit of a polymorphism. We're abstracting away from a specific rule. We don't really care whether it's a user rule or a built-in rule, right? So in both of the cases, we can still acquire, you know, the head of that rule. The problem here is that I copy-pasted a bunch of code, right? So there's a duplicate code between this place and this place, and what if I change the head of the replace rule? What if I change like the way? Maybe I want to change this name. Maybe it's not going to be apply rule. Maybe it's going to be your mom from now on. I should not forget to change that in two places, right? I should not forget to change that into places. So I need to centralize, I need to put that in some sort of a global constant. That would have been ideal, but unfortunately, I cannot construct AST at compile time. It is not particularly constructible at compile time. Because if I remember correctly, where is an expression? I think it's an enumeration expression. Where is an expression? God fucking damn it, mate. Enumeration expression. There we go. Look at that. We have boxes. Can you construct boxes at compile time? Does anybody know? Once cell. Let's take a look at what is one cell. So what I have to do, some people say that I have to use one cell, right? So is this like a box but at compile time? Do I understand that correctly? I'm not a Rust developer, I have no idea. Right, so does it also mean that I have to replace these boxes with one cell for it to actually work? In that case, it's not going to cut it because it's going to require too many changes throughout the code base, so probably not going to go with that. So let's actually go ahead and read about one cell and what the fuck is that. So Rust up doc. It's like what's up doc, but Rust up doc. Extensive API. Okay, so once cell. So let's read std. Well, I mean, I have an old Rust, by the way. I have old Rust. Unlike RefCell, a one cell only provides shared references to its value and Excel. Okay, so does it make it usable at compile time? Oh, not really. Some people say that I can't really use it at compile time. Anyway, it doesn't really matter, chat. It doesn't really matter. Let's not fuss too much about like around it. Right, it doesn't matter. So what matters is that I don't know a way to construct this specific AST at compile time. That's the most important thing. That's the most important thing. I don't know how to construct that at compile time, and I'm not even sure if I give a fuck. Honestly, I'm not sure if I give a fuck. So the easiest thing to do in here would be to maybe construct some sort of a function, right? So we can introduce something like, I don't fucking know, replace head and just return an expression, right? So who said we can't just put that shit in there, right? Who said we can't do that? Mods, ban the person who said that we can't do that, permaban. Right, so apply, where is the apply rule? So I need to find the rule, apply, so apply rule, so here it is, and essentially I can just like put it like that. So, and there you go, I can just, yeah, so that's basically it. So which means that I can do expression replace head, right? So I just use replace head in here, and then in here, what do we use? We use expression replace head in here. And there you go. So we just centralize this entire thing. So we don't even have to think about how do I construct that at compile time, just construct it at runtime. You have runtime. What is this like weird C++ mentality? We have to do everything at compile time. We have the fastest computers on planet Earth, fastest computers in the solar system. We're the only species that have computers, so we have fastest computers in the solar system, and we're trying to still do everything at compile time. Why the fuck do you need a powerful computer if you do everything at compile time? Just do that at runtime. So GS has entered the chat. Exactly, right. So people do be saying like, you have to compute everything in compile time because it's gonna save runtime. And after saying that, those motherfuckers go to their 9-to-5 job in programming Python. And after their 9-to-5 job, programming in Python, they go back and they argue on Twitter how you have to do everything at compile time because it's more efficient. What the fuck are you programming Python? Should've... I'm so sorry. Anyway. I'm joking. Not calling out anyone. It's completely made up, right? This scenario is completely made up. So expression. So don't we have expression macro in here? It's kind of weird. I'm not gonna lie. So it is not in the scope. Macro, I think it's something like macro rules. Here it is, right? So allow unused macros. Why do I allow that? I should not allow that. I don't think I should allow that. All right, so what do we have in here? So so I do quite remember. So yeah, macro use. So that means it has to be exported. And then when I actually did that, it is macro used. Huh, it's kind of weird. I still do not understand kind of fully. Isn't it defined even within this specific module? Where is it defined? Wait a freaking second. Yeah, here it is. It is defined in here. Right, but it's defined below or something? Is that the problem? So macro rules. All right. And then I don't understand. Like how macro is not visible within the... Is this like depends on the order of the definition or something like that? Does anybody know? Macro rules. I'm within the same shit. How is that even possible? I'm gonna try to put that stuff maybe at the top, at the very top. Maybe that will save it somehow. Right, so... That is bizarre, my friends. It is! It does depend on the order of the definition. Holy shit. Or maybe, I don't know, maybe because I moved it up there, it kind of changed the order of the diagnostic of the compiler, because Rust do be like that sometimes, but I would expect macro to work at like any order, like anything. It's just like, really? Is that how it is? Is that how... It is how it is. I'm so disappointed and surprised. Yo, what the... How this thing calling itself a modern goddamn language? I'm really freaking disappointed. I'm really freaking disappointed. Right, is this C? Excuse me, Rust developer. Is this C? How is that a thing in 2023? You were so caught up with making a safe language, you forgot to make a good language. Got him. Oh. All right. So what do we have in here? What do we have in here? So command match defined. Yeah, there we go. So what do we have? So this is rules. We have to pass that by reference. Okay. So what else do we have in here? So we accept 3 arguments, and so what's up with that, mein Freund? What is up? So diagnostic accepts the location, and then, oh yeah, so it's not a variadic. You don't have a variadic methods in Rust. You don't have variadic functions in Rust at all. You can only have variadic macros. That's worse than C, because in C you can have at least variadic functions. They suck. I do agree with you. They fucking suck. But they exist. Anyway, what we have to do in here, we have to do format instead, right? So that's what we have to do in here, because we just can't have this. Though it would be, maybe we could have just like defined a write macro that accepts diagnostic as a sort of, yeah, we could have maybe make like write interface for something. We could define a special structure that holds the diagnoster and the severity, and this entire structure implements write interface. So you could do something like write ln reference to diag, and then you would just put rule name, something like that. But I don't want to do it right now because it's too much intellectual masturbation for me right now. Okay. So it's too much intellectual masturbation for me right now anyway. So this entire thing seems to be compiling. So what is it? What is it now? So name is never used. I see. So I just have to do something like this, right? There we go. So essentially I say name, and I say that name is equal to the name text. Okay, that is very cool. So it should throw a warning, yeah, so that we have unused head, right? So we have unused head in here, and there we go. Here is an unused head. So you know what's cool? You know what's cool, chat? Is that we already have a function that can get a pattern, get an expression, right? And say how, and get the list of all of the sub-expressions that match that specific pattern. We already have that, believe it or not. Apparently I already implemented that. I didn't know that like 2 days ago, but right before the stream I checked it, we actually have that. So let me see. So I think it's somewhere here. Find all sub-expressions, right? Essentially you supply a pattern by a reference with a very specific lifetime, and you supply expression with also reference with the same lifetime, and it gives you the vector of the reference within the same lifetime. So it doesn't clone anything, it doesn't copy any expressions out, it just collects the references from within the expression and gives you the vector of them. Right, so it's sort of like a clone free. Does it even have a clone? It doesn't have a single clone. Right, we can collect all of the sub-expressions that match the pattern completely clone free, right? Isn't it what all Rust developers become very orgasmic about when you like make a complex algorithm and it's completely clone free? It's like, holy fucking shit, it's completely clone free, holy fuck, it's so fucking fast. So that's basically my impression of Rust developers. So you should return an iterator. Iterating tree is kind of a pain in the ass, to be fair. Right, so it's a little bit easier to just collect that into a vector. Right, so we have something like that. So we can actually copy paste this entire thing and go to command. Right, so I'm gonna put it in here. So we do have a pattern, right? So which is basically the head, right? So basically the head. But what is an expression? What is an expression? So I can put something like sub-expers, right? So we're gonna put this thing in here. So, and an expression is only available if we are currently shaping something. Dr. Zoidberg, Rasdev, Dr. Zoisberg, Dr. Zozin. Anyway, so how do we know that we're currently shaping something, chat? How do we know that? Did it become brighter? I hope it become brighter. I can become darker. I can adjust the bag on the top of my lamp and just control the amount of light. I can actually take it off completely and become too fucking bright. So this is basically what I use as a soft light. I can control the amount of light. So, isn't that poggers? Professional setup. Anyways, how can we check for the shapes, right? So this is going to be struct context, right? So we have so-called a shaping stack. Right, so essentially, when you start a shaping, I can probably demonstrate you if, I don't want to run it right away because I'm going to try to recompile it. So maybe I can do something like target, debug, and then knock, there we go. So you start a certain shaping, right? And it pushes the so-called shaping frame, right? And it actually has a counter how many shapings you do right now. You can start a shaping within the shaping, right? And as you can see, the counter is 2. It indicates how many nested shapings you have. You can do some transformations in here, right? So for example, you can say like just extract the first argument, just leave it as it is. And yeah, we have to apply it like that. There we go. So this is what we got, and I can finish the shaping and I can go back to the previous shaping that I had, right? And you can finish it like that. So as you can see, you can have like nested shapings, and a shaping stack is basically that, right? It indicates how many shapings you currently have. You start a new shaping, you push a shaping frame. You start another shaping, you put another shaping frame. So what do we have within a shaping frame? So let me see. So we have the current expression that we're shaping. If you apply different rules, different transformations, that specific expression is going to change, right, according to that. We also have a history of these transformations, right? And we use that history for the undo command, right? Every time you do undo, we actually restore this expression from the history. And rule by shaping is just indicates whether this is just shaping or you defining a new rule through shaping. In that case, we store the name and the head of the expression and stuff like that, nothing particularly special. But what's important, this is the shaping frame, right? So this is the shaping frame. And essentially, what I need to do, I need to check, is there any shaping frame on top? Is the shaping stack empty or not? If it's empty, there is no shaping in place, we can't really match anything. There is nothing to freaking match. Right, so, but if there is something, we have to do something about that. So how do we usually do that? I think we just use the last, yeah, there we go. So this is how we do that. We take the shaping stack and we get the last method, and it gives you the last element, actually option last element. So let's actually go to rust-up-doc, and let's actually go API. And let's find lust. Where is lust? It's a slice. I think slice is also fine, right? So slice is also fine. Show me. Yeah, there we go. So as you can see, it just returns the option. So, and it's very important because if your stack is empty, it's going to be just none. And that's how you know whether the shaping is currently in place or not. So let's take the shaping stack, right? So this is a shaping stack. We take the last and we just pattern match this thing, right? So, and so here we're going to have some shaping frame. So this is a shaping frame, and only within the shaping frame, all of that makes sense. If there is no shaping in place, we have to say something, bruh, there is no shaping in place. I think I already have that somewhere. No shaping, yeah, so I already, as you can see, reported that before, so I can just put it in here. And so we actually have to specify the location. We have to specify the location. I only have the location of the name, right? I can use the name location. So essentially what that means, so how I'm gonna define the syntax of the commands. So it's going to be match something like name, right? And name is a token, and right, so the name log is the location of that specific token. But if there is no shaping in place, what I want to do, I want to point out that there is error not with the name, but with the match command, right? So when I put name location, I indicate that something wrong happened with the name, but this is not true. It makes sense when I couldn't find the rule of that name. As you can see here, I'm using name location, but it doesn't make sense when there is no shaping in place, because the problem is not with the name. The problem is with the match command. So I need to know the location of the match token, and I don't have it in here. That is the problem, chat. That is the problem. So that means within the match command, we need to keep track not only of the name that we're trying to match, but also the keyword. So we can point out of that at that keyword and say, bruh, there's no shaping in place. You know what I'm talking about, chat? You know what I'm talking about? So let's go ahead and freaking do that. So you have a name, but on top of that, let's also have a keyword, right? So, and this is what we're gonna have in here. So that way, so this is a keyword. I can just point out at the keyword and say, bruh, there is no shaping in place. There we go. Okay, so shaping frame, and within the shaping frame, we can extract the expression. So as far as I know, shaping frame, yeah, so it's a structure, which means I can pattern match it like that, shaping frame, and then I can say here is an expression, and then that's the expression that we're using in here. Would you look at that? Would you look at that? All right, so we have sub-expressions, so we probably need to print them somehow, right? I actually want to print them as highlights of the original expression. But I will have to write a special code for that. So I think for now we can just print each individual sub-expression. Let's do sub-expr in sub-exprs, right? Let's iterate through all of them. And let's simply print all of them, right? So I think that would make sense. Simply print all of them. Right, so this is going to be like this, and this is a sub-expression, right? So here is a sub-expression, and that's basically it. I might as well also print its index, but to be able to print an index, I kind of need to enumerate them, right? Which will allow me to do something like this, right? And then I can do something like boom, there you go. Isn't that poggers? Meine Freunde, isn't that poggers? I think we're done with the implementation of the match command. I think we're done with that, so let's try to recompile this entire thing, and boom, it doesn't freaking work because we have to supply all of that shit by pointers. Sure. Still doesn't freaking work because why? So enumerate user behind shared reference, but what's the problem with that? So do we have to do that by the reference as well? Okay. Ooh, since we actually supply this entire thing by value, so replace head constructs a new value, but head in here actually creates a new thing. You can either move it out of there, or the only thing you can do is clone. God freaking damn it, we have to clone it. We can't make this thing clone free. It would be kind of nice if we could construct the replace thing at compile time so I never have to clone, but it doesn't make it easy for us to do. Somebody suggests the refs, but I feel like ref is not going to work because this thing doesn't live long enough, right? We can try something like this, right? So we're gonna try to do something like that. And is it going to live long enough? Yeah, because it's a temporary value. It is a temporary value. So one of these stupid things we can do, we can just make it live a little bit longer, right? We can just make it live a little bit longer, replace head, right? And just return replace head pointer, and that's way, but I mean, does it really change anything? Does it really change anything? I don't freaking know. So I'm gonna go with the original thing because at least it makes a little bit more sense. Right, at least it makes a little bit more sense, and in this specific case I'm gonna just clone it. I'm gonna just suck it up, Virtue Hyper, and simply clone it. Anyways, right, so we implemented match, but we also need to parse it, right? We also need to parse it. So let me see where we can do that. There was a parse command, so okay. So essentially we have different commands, and what we have to do, essentially, we have to have a token for the match, right? So we need to create a new kind of token, a new kind of keyword. All right, so that's what we have to do. So in here, we're gonna have a keyword, which is Alexa next token. Right, so, and, right. What do we have to do? So we need to expect a token ID. I don't really like this particular API for expect because it doesn't really solve anything. Right, so I still have to report everything myself, and it's not particularly convenient. I really don't like this specific API. I would like to have something better. I'd like to have something better. What I like to do in my process lately is have not expect token, but rather expect token several of them, right? So, and essentially that way I can provide an array of different tokens that I expect. So that allows me to just sort of branch out to different things, which is convenient sometimes. So here we have identifier, maybe plus, and maybe you want to pass it by a reference, right? So it's going to be a slice. And essentially, it either returns you the thing that you wanted or it dies out, right? So, and it basically logs the error for you. So that way you can just do something like this and then simply return some command, match keyword name. So it reduces sort of like the noise in the code, right? So essentially here you have a keyword, then here you expect specifically one of these things. In our case, we're going to expect only one kind of token, right? So, but in the future, we may want to have like several kind of tokens. Several kind of tokens. Several kind of tokens. The semicolon. Oh, thank you for reminding me. Yeah, I didn't think I have enough semicolons in here. Yeah, thank you. Right. So, but this function doesn't exist. Right. So this function doesn't exist. So that means we'll have to go and implement that function, right? So we'll have to go and implement that function at some point, right? So, and it has to be implemented in the Lexa, right? So it has to be implemented in the Lexa. So let me just go to engine Lexa. There we go. So, what is it called? Expect le token, right? So here we can have expected, right? So this is expected, and this is diagnosta. And by the way, diagnosta is rather interesting, right? Because it's an interface, right? It's an interface, or how the Rust developers like to call it. It's a trait, right? So they don't want to be associated with that pesky Java. It's not an interface, it's a trait. Yeah, sure, whatever. Right, interface, right. So this is an interface, right. And the reason why it is an interface is that because I thought that maybe in the future I'm gonna have different sort of things for the diagnostics, right? Different things for diagnostics, right? Here we have std_out diagnoster, but maybe in the future we're gonna have some sort of like a window with diagnostics, and in that case it's not going to be std_out. I'm still not sure if I need that, so far I didn't find any application for that, but it might be useful for the right, for like a new REPL which is more interactive or something like that. So but in any case I just keep it like that in here. So because of that diagnoster has to be sort of like a pointer, mutable pointer to an implementation of diagnoster, right? So this is how I would describe that. Right, and expected is going to be a reference to token kinds, right? So this is a reference to token kinds, and this is a public function. So in here we can actually return option, right? So since we're going to be logging the error, we don't really care about specific error. We can just have a result, right? We just can have a result. Right, and in here we can just return a token. There we go. So yeah, what we have to do, we have to get the next token, right? We're getting the next token out of the Lexa. We are iterating through all of the expected tokens, right? So expected kind in expected. If we found the kind that we expect, we simply right away return that specific token and we are done. If we didn't encounter the expected tokens, we have to say, bruh, we expected these tokens but got that one. Do something about that. Right, so what I want to do, I actually want to make it a little bit more human readable, right? So essentially, if you have just an identifier, right, I want to say something like expected, right, expected identifier, but got whatever you got. If you have identifier plus, I want to say expected identifier and or plus, right? If you have plus minus, I want to say expected identifier plus or minus, right? You see what I'm talking about? I want it to be like a little bit more human readable, and I think it's relatively easy to pull off, right? So what we have to do, we simply have to iterate through the kinds in here, right? And we probably want to enumerate them because we want to know whether it's a last thing or first thing and stuff like that. So essentially we're going to be enumerating this entire thing, enumerate, but that probably will require the iter in here. So here we're going to have I, and there we go. So we're going to be collecting that sort of message, right? So we're going to isolate that into something like expected message, right? So expected message, it's going to be a mutable string, right? Because it's sort of like a buffer into which we're like building and collecting everything. Right, and if I is equal to 0, right, if it's the first thing, if it's the very first thing, we just have to specify, we just have to append that name into the string, right? So that's what we have to do. We have to just append that thing. I wonder how easy it is for me to do. I don't quite remember. So what kind of methods do we have in string? Do we have something like push str or something like that? There is insert str, but there's something like push str. There is something like push str. Right. So we want to do something like expected message, push str. All right, so what do we have in here? So I know that in token we have token kind specifically, we have display implemented for it, don't we? Display for token kind, there we go, that's what I'm talking about, right? So this is a token kind. Display for token kind is probably what I want to have in here. Is it possible to write into a string? Does string implement a write interface? Does anybody know in this Rust community? It does implement write. Would you look at that? Where is it actually implemented? It's implemented somewhere in FMT, or is it just like, yeah. So it's inside of the std string. I don't know if it's available out of the box, but that means I can do some pretty epic scheisse. For instance, I can say expected message, right? So probably have to pass it by some sort of like a mutable thing or something. We'll see. And I can just do kind. That's the stuff I can do. Isn't that poggers? I think that's pretty freaking poggers. All right, so the other thing we want to do is to check whether this is the last element, and the easiest way to check that is probably I plus 1 is equal to expected len. And in that case, how do we end this entire thing? We end it with or, right? We end it with or. Otherwise, this is something in the middle, and in that case, we just do that with a comma, right? So we just do that with a comma, right? So after that, we have the expected message, which we can simply print, right? So this is going to diag report. So what do we have to do? So we need some sort of a location. Location is within the token, right? So this is the location. Severity is error. And what do we say in here? We have to use format. Expected message, right? Expected message, but got actual, right? And we can say that the actual is equal to token kind. That's how can we approach this entire thing. And of course, after that, we want to return none, right? Because that's the indication of an error. So I want to have something like that. You know what I'm talking about? You know what I'm talking about? I want to have something like that. That would have been kind of poggers. All right, so let's try to go ahead and maybe compile this entire thing and go to the compilation errors and everything. So we don't have diagnostics in Alexa, which is kind of strange. So let's go ahead and maybe import them. So this is going to be super, right, engine, and maybe just diagnostics, there we go. So this is what we want to have. What else do we have in here? So self, oh yeah, we have to actually pass the self in here, and it has to be a mutable pointer to self. Would you look at that? And of course, this entire thing is a pointer, so I suppose I want to actually dereference this thing. What else do we have in here? So no method write fmt found for mutable reference string. Okay, so that's fine. So that means I need to find the implementation for the write. And the question is where it is located, right? So where is FMT, where is the write implementation is located? So let's probably have to maybe use std string right? Is that what I have to do? Right, no, this is not how it works. Maybe it has to be FMT right then. Maybe that's what we have to do. Anything else? Expected, oh, okay, wait. But found result, interesting. So that means maybe, like, I suppose writing into a string is probably not gonna fail. I didn't think it's gonna fail, right? So we can just put semicolons in here. So I didn't think it's that big of a deal in here. Right, there we go. So the match, a match. Oh, there's no such keyword. All right, so let me see. So we need to introduce the token kind. All right, so let's go ahead and introduce the keyword called match. So we introduce the keyword match. So it's going to complain about some things in here because of that. So safe. This is going to be match, and that's the keyword. What else do we have in here? Okay, so we have some. So it's never constructed, I see. So this is because we probably want to have implementation in here. So if you encounter a sequence of characters match, this is a match token. Treat it like that. Okay, thank you very much. So this thing is never used. That's understandable. Variant match is never constructed. That is also understandable. So what else do we have in here? Unused result must be used. God freaking damn it. Okay, can I just do something like okay? Right. And something like this. Is that something that is viable? I feel like it is kind of viable because I feel like it's never gonna fail. Like, in which case it's gonna fail? When it cannot allocate memory for the string, I suppose, right? So do Rust developers actually check for memory allocation? Maybe they do. So in that case, well, in that case, it's not going to even report an error if we do it like that, so I didn't think it's a good idea. So it's better to like straight up unwrap, because I literally don't expect this thing to fail. And when I don't expect something to fail, unwrap is what you probably want to do, right? So that makes sense. Right, so that makes sense to me, at least. So match, we never constructed match, so let's go ahead and construct the match token kind match. What do we have in here? And of course, let's do it like that. There we go. So, something, wait a second, where is my, yeah, there we go. So this is what I wanted. This is what I wanted. Okay, so I have a name, and what I have to do is just construct. Okay, so let's actually see if it compiles or not. Right, so we have, oh, we have an extra semicolon. I'm really happy that the compiler is here to help me and explain me that I have like extra semicolons, so I don't have to think about it too much myself, so I can just go ahead and remove it. That's very useful, that's very convenient. Anyways, so let's continue. So we have it has to be mutable, right? So I suppose it has to be mutable. So diagnoster is not satisfied, is not implementation trait for, ooh, right, but wait a freaking, oh, because it's already a mutable thing. Okay, I see what's going on here. I see what's going on here. Boom. We hopefully fully implemented the match command, right? So we fully implemented the match command. So let's go ahead and see if we can just run it and play with it and stuff like that. So let's go ahead and load the entire standard library. So the entire standard library, let's take a look at it. It includes all of the proofs that we wrote in the previous stream. Like all of them, I put them in the standard library. So we also have some extra stuff, some extra interesting stuff. Like for example, I defined subtraction, right? And defined some properties on the subtraction and actually proved them. Right, so for example, difference ID, when you subtract a number from itself, it's equal to 0, and I actually proved that mechanically, and it was relatively simple actually, relatively easy. So anyway, we can go ahead and load this entire thing. So it's going to be std knock, and there we go. So all of them are loaded up. We have a lot of different properties, different things we can play with, which is rather convenient in my opinion. Right, so what we can have in here, so let's actually define some stuff. So a plus b multiplied by c. Here we can do plus d plus e, right, multiplied by 5. So we have this kind of thing. And essentially what I want to do, I want to try match, right? So, okay, so that's pretty cool. It detects that I didn't fully provide, right? So it expects identifier. We can provide identifier that doesn't exist, like your mom. Rule your mom does not exist. Okay, so that's cool. We can do some ID, and it did nothing, right? So some ID, well, it makes sense, right? There is no such some ID in here. Right, so what we could have? We could have probably some com, right? So commutativity. Let's actually try to match that one. There we go. Okay, so this is interesting. Ooh, this is pretty cool. So 0 matches this entire expression. Very important. 1 matches this one. 2 matches this one. That's already useful. If I want to swap around this specific thing, I know that I have to use 2 in here, and boom, it did exactly that. So that's already useful. That's already useful. But unfortunately, it doesn't show them in a context, right? It doesn't show them in a context. For example, if I had something like sum ID, well, I need a reverse of the sum ID, right? So that's the problem. I need the reverse of the sum ID. Maybe some, I don't have it. And there's no way for me to say match some ID. Maybe there should be a way to say something like that. There should be a way to actually say something like that, because you can apply the rules in reverse, right? So I can do something like some ID, right, and reverse it on the second one, right? And this one didn't really work the way I expected, but I mean, yeah. I need a way to say match, but with the reverse. That's definitely something I have to do. All right, so let's go ahead and implement that, right? So since it's something that I need to do, I need to implement that. So this is how I design the features, right? So implement a little bit, then try it and see what's missing, and implement what's missing. Pretty straightforward stuff. Pretty straightforward stuff. So in here, we probably want to have a special field called reversed, and it's going to be a Boolean, right? So it's going to indicate whether you want to reverse this specific rule or not. All right, so in the syntax, I suppose is going to be match. If you want to just use the thing, you provide the rule. If you want to reverse it, you provide the bang, the exclamation mark. As far as I know, for the bang, for the exclamation mark, we do have a separate token. Let me take a look at the token kinds. Do we have a bang, 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 bang? There we go. So this is a special character. It's called bang. We can actually use that. That's pretty useful. All right, so parse, match. Okay, as you can see, after the keyword, what we have to do, we have to take, maybe we have to pick token, right? So we have to pick into the next token. Let's call it bang. So this is a potential bang. If bang kind is equal token kind bang, we have to reverse this entire thing. We have to reverse this entire thing. And we might as well get rid of that token as well. So essentially what we're going to do, we're going to do Lexa next token, right? So because pick doesn't remove the token from the Lexa, it only picks into the token. It only picks into the token. So if we encounter bang, we have to get rid of it. So, and after that, we're going to return true. Otherwise, we probably want to return false, right? And this is essentially reversed, right? So this is reversed. To be fair, we don't really keep track of the bang too much, so I suppose the easiest thing here to do would be to just inline this stuff, and there we go, so we have reversed. And then we can simply use that reversed in the definition in here. There we go. There we go. So then, when we are actually interpreting the match command, we need to take a look at the reversed. That's pretty cool. And this is actually pretty cool. All right, so here is the expression that we're using to match. All right, so I would say it's a pattern, right? So this is the pattern. And that's the pattern that we're using here. And here is the trick. If we want to reverse, the pattern that we're going to be using actually is the body. Otherwise, it's going to be the head. But in case of the replace, I think replace is not reversible rule. Reversible. Yeah. So we even have this kind of error. So in a different context. So, and in that specific case, that's probably what we want to say, right? If you're trying to reverse the built-in rule, you should not be allowed to do that. Right, so we're going to say something like this, and I'm going to instantly return none. Right, you're not allowed to do this kind of stuff. Otherwise, we just use a replace head. Okay, so and that's the pattern that here we match everything, and now I can actually reverse the rule that I'm trying to match, which is rather convenient, I think. So let's go ahead and try to compile this entire stuff. Of course, go to the compilation errors. That's why we have statically typed compiled language. That's precisely why. And in here, so this is the location. Right. So what kind of location do we have to use? I suppose we have to use the location of the name, right? So that makes sense, right? So we have to use the location of the name. And there we go. That's pretty cool. So let's restart this entire thing, and I'm going to reload this entire stuff, and I'm going to have like a big expression that we had before, this one. So, and what I want to do, I want to match some ID, but in reverse. And that results in a lot of different sub-expressions, and it is absolutely unclear what the fuck is going on in here. Well, in case of like very unique variables, it does make sense, but imagine that if each individual variable was A, that would have not be clear like which A we're talking about. I can probably even demonstrate that. So let's actually go ahead and replace all of them with A just to see how ridiculous it's going to look like. Right, so there's going to be match, some ID. Like, what if I'm going to do for which A I'm going to replace? What the fuck is going on? What the fuck is this shit? You know what I'm talking about, chat? You know what I'm talking about? That's exactly what I'm talking about. There is no context. Yes, it is a sub-expression, but where is the context? I want to see a freaking context. You know what I want to have? I want to have a full expression. I want to have a full expression, but the specific sub-expression that needs to be reversed, highlighted. That's what I want. That's what I deserve as the developer of this program. Right. So I want it to be highlighted. And you know what's interesting is that this is something that I implemented quite some time ago for the new repo. I even use Termion for that. Do you guys know what's a Termion? Let me actually see. So Termion. Have you guys heard about it? Have you guys heard about it? Right. So crates.io. Crates.io Termion. So it's a bindless library for manipulating terminals. It's a very manipulative library. So essentially, it allows you to have, at least in my case, callers in a terminal in a very cross-platform way. At least this is how I understand that. Right. So, and this is what I already used for highlighting sub-expressions. So in a new repo, I have an interesting thing. Yeah, highlighted sub-expression. There we go. So it's a special structure that points at the full expression, the root expression, and the sub-expression within that expression that needs to be highlighted. And this thing implements its own display interface. I'm going to call it display interface because that's what they are. This is just interfaces, right? I don't care that you Rust developers want to be special. No, this is not interface. This is traits. We're special. We're not like Java. I don't give a fuck. This is interfaces. Cry more. All right. So, and essentially I have a special implementation for that specific interface. And when it basically does the traversal, the recursive traversal, right? And when it matches the sub-expression, it uses the Termion magic to highlight it with a specific color. In that case, we're using green. but that doesn't really matter. We can use whatever color. I think green is fine. Green is not a particularly creative color, but I think it's fine in this particular use case. So we can try to do that. So is this thing public? I think we need to make it public. And I'm going to be using the new repo in here. So I wonder if I can just use something like super new repo highlight sub-expression. There we go. Highlighted sub-expression. The way you're supposed to use that is very interesting, mein Freunde. It's very interesting, mein Freunde. Let me find the place where we do the iteration, right? So this is where we do the iteration. And we have original expression, right? And the sub-expression. The names even match. That's actually pretty cool. Even the names match. And then I can say, okay, sub-expression is this thing, and theoretically it should just work. Yeah, it actually should just work. Pretty interesting. Pretty interesting. So let's try to, yeah, first try. Right, so I'm just reusing whatever I already had for some time. All right, so I'm gonna try to maybe I'm gonna just select this entire thing that I'm gonna load. This entire thing, I'm gonna copy paste this stuff in here. Okay, and then I'm gonna do some ID match in reverse. I already had this thing implemented. So when this is weird, like why is it highlighted like that? I think I know why. I think I know why. Because the way I compare, right, the way I compare is literally with equals equals. And at the time, I thought that it would compare references in a sense of like the pointers. Right, so, but how do I do that? So that's the real question. How do I do the pointers? Can I take, oh, here's the interesting thing. I remember that in Rust, you can take a pointer to something, to a reference. You can convert reference to a pointer, and that is not considered unsafe thing. Right. That is not considered unsafe thing because you're not dereferencing it. Right. So let me actually Google that. Rust reference to pointer. Right. I think taking pointer is not like an unsafe thing on its own. Pointer types. So there is also from ref. Why is it nightly only experimental? Right, and as you can see in here, oh, it's a const. Okay. So pointer types, there's too much text. I just need the confirmation that it's not unsafe. So, but in any case, we can just try to do something like as. So there was some things in here. So this is equivalent to that, but a bit safer. It will never silently change type or mutability, in particular if the code is refactored. Okay, so as const and expression, right? So, and then as const expression. So that's probably what we want to try to do. Is it going to compile? It is not going to compile. Casting, this is invalid. So, and the second one here, both of them are considered like a double reference for some reason. This is actually kind of strange. Is that because, okay, so that's pretty funny. What if I dereference these things like that, right? So, okay, so it is a safe operation. It's kind of funny. Row pointers are safe as long as you don't try to dereference them. Yeah, makes sense. Okay. So let's go ahead and try to do that. So we actually caught a bug, basically. All right, so let me try to match this, and there we go. So here are all of the matches in here. So for instance, I want to specifically, you know, add 0 to sort of like this one. I want to add 0 specifically to this one, which means that I have to do it like this, right? So this is that. This is the 6th one. There we go. This is precisely what I wanted. This is very useful, right? Because I used to like have a lot of trouble just like trying to substitute something and then undo and try do it again, and it's just like so inconvenient, honestly. It's just so inconvenient. So it would make sense maybe for like with this thing, right? So I want to swap specifically this, right? I want to swap specifically this, and because of that I can just use F3 and it works exactly as I expected then. Okay, so now I want to swap you know, something else, maybe the whole thing, right? So that means some commutativity, right, it's gonna be 0. There we go. So, and then I don't know, I can do some other things, maybe some ID. Is there any match for some ID? There is match for some ID, so that means I can apply it. Right, so for 0, is there any match for some ID? No, there is no matches for some ID. That's pretty cool. So it's a little bit unergonomic. It is in fact a bit unergonomic. What if, and this is a very cool idea by the way, chat, what if instead of a separate command, this was a strategy? Holy fuck. Because this is a huge problem, believe it or not, right? So I want to do match but reverse, right? So essentially I do match reverse, and I'm picking like what I want to modify. Okay, I want to modify this one, it's the 6th one. So now, how do I have to change this entire thing? I have to change it like that. I have to remove this entire thing. I have to bring the reverse in here and put 6 in here. You see, transforming from just match to actual rule application is too much effort. It's not ergonomic. You know what I'm talking about? It is not ergonomic whatsoever, right? And I need to be able to switch between show all of the matches and apply the rule, show all of the matches and apply the rule all the time. What if instead of this thing being a command like this, it was a strategy? So I can do some ID, but show me all of the matches, right? Show me all of the matches. Then I can pick the match, and then I can say, okay, do that on the 6th one. So the amount of changes I have to do to switch between match viewer and the actual application is minimal. I just changed the strategy. I think this is way more ergonomic. This is way more ergonomic, right? Because whatever we have in here is absolutely unergonomic. Like, yeah. And you know what's interesting is that I'm not planning anything of. I didn't plan any of that ahead. I'm just trying to implement something. I just throw in something at the wall and see what sticks, right? So for example, I implemented this thing and I noticed it's not convenient to use, and I got an idea how I can improve it, right? So that's how we design things, right? So they kind of naturally design themselves, right? So yeah, I gather information by implementing things. And problems become obvious, and you just fix the problems. You just fix the problems. You just fix the problems. Okay. So, but I think before I do that, I would like to make a small break and make a cup of tea, chat, right? Because I've been streaming, been slapping code for 1.5 of an hour, and I ran out of tea, and I need tea to survive. So let's make some break, and all right, I'm back. So let's go ahead and try to implement this thing as basically one of the strategies, right? So the command that we use for applying the rules, is called apply rule. Okay, so that's pretty cool. So, and then we have a strategy name, right? So this is basically the strategy name. So we need to find command apply rule, right? Command apply rule, and where do we try to interpret that specific command? This is where we try to interpret this entire thing. All right, and that's where we have to do all of that. So interestingly, where is the strategy? Yeah, we get the strategy by name. We get the strategy by name, and that's where it is very interesting, because we have kind of predefined strategies that you can use for rule and stuff. Right. So there's all, deep, and nths. But what's interesting is that the strategy that we're about to add, it's a strategy specifically for the shell. So I'm not sure how exactly we're gonna go about that. I can probably add match, but it's not a real strategy, so to speak. It's not a real strategy. Because of that, I'm not quite sure how exactly I want to go about that. Right, so it's a by name, so it's a X. So there's also first. This is actually kind of cool. I didn't know that I had a strategy called first that just picks the 0th one. Yo, that's kind of funny. I don't remember adding that strategy, but okay. So I'm not sure how I want to go about it. So I could have just compared first to the text, but I think it would be easier to just like add the match. Right, let's actually add the match. This is going to be the match, and this is some self match. And let's just go to the compilation errors and see how we're going to go about that. Right, so, and here, by the way, we can have some interesting stuff. So we can have a strategy which is match, so it's going to be handled differently. Right, and if it's not a match, it's something else. I think that's how we can go about that. That's how we can go about it. So let's go through the compilation errors and see how it's gonna go. Right, so, and when we are matching some stuff, right, we have to make decisions. We have to make decisions according to the strategies. And this is exactly why I didn't want to introduce like a new enumeration, because this enumeration doesn't make sense in this specific context. It doesn't make sense, right? So it has to be unreachable. Right, so, and maybe self match should not be a thing. Right, so I'm gonna even make it some sort of a to-do, because the fact that I have to use unreachable in here kind of hints that this enumeration just simply doesn't make much sense. Simply doesn't make much sense because it's a special thing, though it compiles fine, compiles perfectly. And this is where we can do all of this match substitution magic, right? So let me find the match command. So, and obviously we already checked, right? So when we're applying the rule, we already check for all of the shaping that is currently going on, because as you can see, we're already taking the shaping frame and stuff like that. So we don't have to worry about that. Everything is already checked. The only stuff we have to do, I think we already even have the rules prepared. Right, so we even have the rules prepared, like by name and stuff like that. Yeah, so we literally already have the rule. Like everything is already prepared, so I can just use that. I can just use that. So I can copy paste this entire thing. Right, and put it in here. And so the pattern is basically rule head, right, and expression is a frame expression, and that is basically it. Wait, is this really it? That is too easy. I can't believe it's that easy. It can't be that easy. I do not believe you. Right. So okay, so here is a sub expression, but that just means that I have to use frame expression as a sub expression, so I suppose it has to be maybe a pointer like that. So is it going to work? So it doesn't like the head, no field head in rule. Are you sure about that? I quite freaking I see. Okay, interestingly, we already checked for all of this. Damn. We need to be able to take not only the rule itself, but also its head, so it's not that easy in this specific context. It's not that easy in this specific context. So if we take the replace, so we can just do that. Man, we can try to maybe return head like this. It's gonna be very ugly code. Very much ugly code, but it is what it is, and it isn't what it isn't. So, okay, if we're returning head as well, body becomes the head, but we'll have to clone it, I suppose, right? It has to be cloned. In case of the replace, we can't replace it, so it doesn't matter. So this is when we're trying to reverse it. If it's irreversible, we still need to check. Oof. We still need to check. You know what would be good? We need to take that idea of sort of like a head, of polymorphic head that we have in here. Yeah, this one. Haha, this one. So here, as you can see, here we essentially matching the rule, and if it's a user, we return head, otherwise we return replace head. I feel like we have to introduce a special thing specifically for that. We need to take that idea and factor it out into its own function. Right, it needs to be factored out into its own function, otherwise it doesn't make much sense. Where is the implementation of expression? Here it is. So this is just a replace head. This is just a replace head, but I would like to have something like just head, which may work, right? So which may work. So we take this thing by a pointer, right? So this is just the head. It returns the expression, but it's going to return a different thing depending on what kind of expression do we have. Is that a user expression? Right, in that case, it's just the head. We just clone it, and there you go, we've got that. If it's a replace, right, it has to be expression replace head. There we go. Which is rather interesting. So what's the second place we use replace head? It's somewhere in rules, replace head. Yeah. And the reason okay. So maybe we can reuse that, but all of that is for later, right? So we can do that a little bit later, but generally that's probably what we want to have in here, which will allow us in the future, to do something interesting. All right. Okay, so here it is fine. So here we can just keep it as it is. Right, apply rule. Where is the apply rule interpretation? Right, we just have the rule, but if we need to match it, right, we just do rule head. That's right. So, and since, okay, so that's totally fine. That is totally fine. Oh, right, so this is just that. What else do we have in here? No variant. Oh, okay. This is not expression, this is rule. Yeah, this is rule. So I have to find the rule, implementation of rule. So here it is. So this is the head of the rule. So that's what I actually wanted in here, right? So, and because of that, this becomes rule. This becomes, yeah. That's fine, there we go. What else do you want from me? Temporary value is freed at the end of this step. Get freaking that, okay. So we probably want to do something like head and just head. So it's lifetime situation. There we go. I think we managed to compile this shit. So this was hard. This was hard, just like myself right now, but we managed to do that anyway. So, okay. Gotcha, Hyper, I know. Let's go ahead and try to do that. Where is this thing? And let's reload this entire scheiße. There we go. And now what can I do? I can do some ID, invert, and I can say match. So applied strategy must be identified. God freaking damn it. Just because I introduced match keyword, I can't use it in here because it has to be identified. I have to go ahead and okay, so let's try to do something else, right? Now I have to remove this entire thing. How do I remove that? I don't want to remove the command match because I feel like maybe it's going to be useful in the future. But it looks like I have to. Okay, so let's actually go ahead and just remove the keyword. We were adding the keyword, but now the time has come to remove it, right? It's not useful anymore for us. Let's go to the compilation errors. It's not too hard to do it like that. It's totally fine. Don't worry about it, chat. Don't worry. So where's the match? Here is the match. Boom. So what else do we have in here? So expected tokens are not used anymore, but this is a thing that could be used in the future. So I'm gonna allow it to be dead a little bit. I'm allowing it to be dead a little bit. So what else do we have in here? So we don't need this stuff anymore because we're doing that through the apply thingy. So, and this one, yeah, is not needed anymore. So it basically removed everything that I implemented through the entire stream, but the actual idea, yeah, I just realized that I removed almost everything I implemented throughout the stream. That is funny, actually. But I mean, I implemented all of that just to discover the way I want to implement that feature, right? When I started, I thought that having a command was a good idea. But once I implemented it, I saw its flaws and I came up with a better solution. So I didn't waste time. I gathered information. It's not a freaking copium. This is how you do software development. How is that a freaking copium? Mods? This is literally how you design systems. You try to implement them and you see that it doesn't work, you change them. You don't waste time, you gather information. What? Okay, anyway, so let's try to see what's going on. Right. So let's go. So I'm gonna copy paste this entire thing. Load the entire scheiße, and there we go. All right. So some ID is gonna be like that, and give me the match. Look at that. So then I can say, okay, I want to add 0 to this specific A, and that specific A is at index 9, and there we go. I have a really fine control over how I can transform shit. That is absolutely poggers. Right, so and I can control whether it's going to be reversed or forward. In case of a forward, right, so in case of a forward, like I don't think I have that much. Oh, I do have some control in here. Huh. Ooh, and this is very interesting. So after applying the strategy, it prints the current expression, which doesn't make sense in case of the match. I think it doesn't make sense. Apply a rule. Right, so let me do something about that, chat. Let me do something, because yeah, this is where we do all of that. Maybe we want to put it somewhere here. Yeah, like this. Right, we're only gonna print it when we successfully like identify this strategy, right? So it's not like a fake strategy like match, and we successfully apply it and push it to the history. In case of the match, we don't want to print that, which hints even further that match should not be its own strategy. It should be sort of like a stopgap, if that makes any sense. some sort of a stopgap. All right, so let's give it a try one more time. All right. I'm gonna grab this entire thing and I'm gonna load this entire stuff. Boom. Yeah, we need to start shaping some ID in reverse match. I can try to do sum and see what matches in there. Can I do sums in here? Nah. So if I want to do sum, so this is the match. I'm gonna add this thing in here. Then I can try to see if I can inverse some of the stuff. No, I can't really inverse some of the stuff. But yeah, sum ID. I can apply it in here. Yeah. So yeah, it's kind of cool that I have this level of fine control. This is very, very cool. So we have an interesting question. Would you ever use Golang for writing a compiler? I used Golang for writing an interpreter. Does that count? Does that count? So some time ago, I implemented Markut, which is basically an interpreted language for editing videos. Believe it or not. It's an interpreted language for editing videos. So essentially, it allows you to do the following things, right? So it has the concept of chunks and stuff like that. So I think I can demonstrate it. So essentially, you have some sort of input footage, right? Some MP4, and you do it like that. So essentially, it's stack-based, like Porth, right? It's stack-based, and you specify the input like that, right? And then you start specifying chunks, right? So you specify the a time stamp, right, starting from 00 up until 5 minutes, right? So this is the first chunk. Then you can specify chunk 5:10 up until like 6, right? And this is the program. You feed that program into the interpreter, and the interpreter actually on each chunk will call ffmpeg and cut it out, re-encode it, and then at the end it's gonna concatenate all of these chunks back. Right, so, and it can do a lot of different things, right? It allows you to customize stuff, or preview cuts and stuff like that. So, and it's written in Go, right? So it has its own Lexa, it has its own parser, and stuff like that. So it's an interpreter written in Go. Does that count? Does that answer your question, right? You can do whatever you want in any language, right? So it doesn't really matter. So I'm going to put that in the description for anyone who's interested. So there we go. Okay, guys, so we have a matching thingy. And it's actually extremely convenient. It is actually extremely convenient. You know what would be cool? We, like in the standard library, we're starting to have a lot of rules. And I haven't even started yet, right? I haven't even started yet, but that's a lot of different rules I already specified trying to prove different things. I need a way to quickly you know, filter out irrelevant rules. So, and I think we should be already able to do that. We should be already able to do that because essentially I can have the current shaping expression and I can ask the question, show me all of the rules that match at least one sub-expression within the current expression. Right. And you can basically filter out this specific rule and get the list of them. That would have been useful. So you can basically identify, okay, so here are all of the rules that kind of can be matched in here. And then you can take the rule and see what sub-expressions exactly you can match with that thing. I think that would be useful. Think that would be useful. I wonder how much time it will take to implement that, because I can try to implement right now, but I will definitely go over 2 hours. I definitely will go over 2 hours. So that will definitely gonna be some sort of a separate command, right? So we can repurpose the match command, but this time without any argument, right? So essentially it will be kind of cool so that you have this sort of expression that you're currently shaping, and you can say, okay, show me all of the things that match at least one thing in here, right? Just show me all of them. And then you would see all of the rules. Okay, those rules match. I can pick that specific rule, like some ID, and just ask, right, what are the sub-expression that specific thing matches there? That would be interesting. That would be interesting, and it's not that difficult to implement, actually, believe it or not. It's not that difficult to implement. It's just the question of how we're going to do that syntactically. So I could use match, but we already used the word match for this thing, so we need to come up with a different name for that command. How can we do that? Search, it's kind of misleading name, to be fair. Search is kind of a misleading name, in my opinion. It's definitely going to have a keyword, because we'll need to report an error in case. Maybe fit? Yeah, something like fit. Yo, we're going to call it fit. I think that's perfect. I think that's perfect. And in Alexa, we're going to have a fit keyword. So that's one of the things we want to have. So where is the save? So here is the save keyword, token fit. So this is the keyword Alexa next le token, and we just return some self, what is it called, a fit keyword. So that's how we're gonna approach all of that stuff. So, and then save command. So this is the command fit. So this is keyword. And we need to check whether we're currently shaping. So here we have a frame. All right. So this thing is not implemented yet. Shaping, no shaping is in place. So how are we gonna go about all of that? In the frame we have the current expression. We need to ask a question like, does a particular pattern match at least something in there? Interestingly, it doesn't search reversed things. Maybe it should also search a reversed thing, but we have to display them somehow differently. And maybe maybe we need to have a special method for the rule. So we already have a head. Maybe we need to have reverse. Why didn't I, wait a second, why didn't I implement the reverse as a method of rule? Why didn't I think about that? That's actually perfect. I think I'm a dummy dum-dum, chat. I think I'm literally dummy dum-dum, but it is what it is and it isn't what it isn't. So self, might as well, whatever, doesn't really matter. Rule, so this is the user. So that means head becomes body. We kind of have to clone it, honestly. And the body becomes the head. In case of the, and you can't easily do that because it's, in case of a replace, it's irreversible. So this has to be sum, and then rule replace, right? In case of that, it's going to be none. It's irreversible. It has to be reflected like that. So, yeah. For each individual rule that we're going through, right? So we need to go through all of the rules essentially, right? So let me take a look at the struct context, right? So where are the rules? Here they are. So here we have a name. We don't care about the name, only the rule definition, okay? In self rules, it's going to be iterator, and we have a rule definition in here. And we can take a look at some rule definitions. So maybe I'm going to do rule definition. I don't care about the rest of the stuff. I don't care about the history. I only care about this rule specifically. So the question is, does this rule fit? We do care about the name because we're going to be adding that name into the thing, right? we're going to be at least printing it, I suppose. Okay, so we have a rule, and we probably want to take the head of this rule, and we want to ask the question. So this is the pattern. So we have a function in expression, find all sub-expression. We need something similar to that. It should probably even accept the same arguments, but it should return Boolean. So, right. So, matches at least one, right? So, essentially, we need to see if this thing matches at least something, right? And it instantly returns a true. So essentially, it has to recursively traverse all the sub-expressions and see if something matches there, and if it does in fact matches something, we should return true. To be fair, it could be it's basic. We have to basically copy paste this entire thing, to be fair. All right, so pattern match. So maybe this is how I'm gonna go about that. That's very interesting. So essentially, if the pattern matches expression, we instantly return true. Just instantly return true. Otherwise, we have to do something else in here. So we have to rename this stuff to matches at least one. Right, so that's how we go about that. So we supply the head, the pattern. Why do we have to do it like that? I'm not quite sure. So we're collecting sub-expressions. So in that case, we don't really care about them. Right. So if, and this is the funny part, if this thing is true, we have to instantly return true. Yeah, so essentially, as soon as at least something matches, we have to stop the recursion. Right, at least something matched, just stop the recursion. Right, and so nothing matched. So here we can just return false in that case. Yeah, there we go. That makes sense, I suppose. Matches at least one, so this is going to be very useful. So let's go to the commands. Well, where is the commands? Here's the commands. Right, so matches at least one. We provide the rule. Probably pointer. So that's the rule. And what we're trying to match, we're trying to specifically match the expression. Right, so we're trying to match the expression. If it matched, we have to print it. So it's going to be print ln. Something like this, space name. Right, so this is going to be the name, and name is basically the name of this rule definition, but text. And here comes something interesting. We also need to try to match this thing in reverse, right? So let's take the rule, reverse the rule, and take the head of the rule, right? Take the head of the rule. But the problem is that rule might not be reversible. So that means we have to check for that. So if so, Jesus Christ. Thank you for the alarm. Yes. So that means I need to finish the stream soon. The KGB, yeah. All right, so some rule. And we just do rule reverse, right? If it is reversible, I think this is how we call it, right? So where is the rule? Yeah, reverse. If it's reversible, we do that thing one more time, but we're gonna indicate that it's reversed. So we're gonna put some exclamation mark in here to indicate that. And that's about it, I think. That's about it. Okay, so that looked good to me, I suppose. What else do we have in here? So return true. This is not... Ooh, Rust! Fucking Siri, I forgot about this shit. Why are you like that? What? Oh my god. Yikes. freaking yikes. Sure, buddy, sure. I mean, we could have made it sort of like a option, and that would kind of help, I think. You know what I'm talking about? So essentially, a return sum, and well, I mean, it's not gonna work that well because it's just easier to do it like that. Okay, so it's kind of dumb. Goofy boolean. It would be kind of cool if you could do question mark but with booleans. That would be kind of interesting. That's an interesting idea actually, but it doesn't really make much sense, I think, in the context of Rust. All right. Goofy, silly ass Rust. So that's what you want. What do you want from me? I don't freaking know. Use a comma. Okay. All right. So what do you want from me in here? Expected boolean, but got really what the freaking what? Expected boolean because of the return time. Expected boolean because of the return type. So here, but how is that a return type? Can I just do something like false in here? Right, because in all these cases, this is gonna be just like unit. Why can't I do it like that? I think I can. Okay, so I can do it like that, sure. So semicolon, would you look at that? The compiler actually warned me about that. So we have to add a fit in there. So we're trying to fit some stuff. These nuts into your mouth. Oh, got him. Okay, so save fit. All right, there we go. What else do we have? So did we fully implement what I wanted? I think we did. I will actually put extra space in here. I think it's going to be very useful. All right, so are you guys ready? Are you guys ready for some epic action? Right, so we're going to restart this entire thing. I should have actually done something like cargo run, just in case, so it rebuilds everything. Then load, and then I could not load. What I wanted to load is std knock. Okay, so let's put this stuff in here, start shaping, fit. So all of these things fit actually. That's kind of cool. So that means I can try to be fair, this is not particularly ergonomic, right? If I want to just try to apply this thing, I have to do it like that. Right, so this is the match. So a sock, yeah, this is where you can apply it. That's pretty convenient. So this is basically everything. Yo, but where can I apply the difference? I mean, it's a reverse difference. Oh, and I can apply 5. This is actually kind of cool that I can apply 5 in here. Yo, that's so funny. Right, so it saw 5, right, and it tells me that I can apply 5 in here, so that's so cool. Right, there we go. That's kind of funny. Let's try to actually prove simple things, but with the new features that we just implemented on today's stream, right? So we'll need reflexivity, of course. We're going to start from scratch, right? So this is reflexivity, this is true. So sum ID, let's define this thing. This is going to be 0 plus a equal a, so we have that. Just sum definition is s of a plus b equal s a b. Right, so we may want to define some things in here. So this is going to be 2 equal s of 0, right? So let's define that. Let's define 3. So that's extra s. Let's do 3 plus 2. Boom. Fit. Okay, so we can apply 2. Reverse ones are actually kind of distracting, so I'm not sure if it's particularly useful, but we can work with that. Then fit, yeah, 3 first. There we go. So what fits in there? Some fits in there. Yeah, reversed one are kind of distracting. So I feel like we need to have a reversed one as a separate mode. Right. So, yeah. Because this is something that you don't want by default. It is useful, but this is not something that you want to have by default. So because of that, we probably want to introduce something like reversed, right? So this is going to be Boolean. And we can denote that with fit exclamation mark, right? So because exclamation mark is reversed, right? So fit, and in here we're going to do what? If Lexa pick token kind equal token bang, a token kind bang. Right, so let reversed. True, but first we also have to do next token, right? So this is the next token. Otherwise, it's going to be false. And here we just do reversed. There we go. So what else do we have in here? So excuse me, did I do a fucky wacky? Huh? Oh yeah, Jesus Christ. Okay. So reversed. All right. So if reversed, we can simply copy paste this entire thing. We simply copy paste this entire thing, but we used the reversed rule instead of the usual one. But in the usual case, we use that one. Boom. It's that simple. Anything else? All right. Boom. Okay, so let's start with the reflexivity yet again and see what kind of usability problems we're gonna encounter. Right, so far, I think there should be no usability problems, but you never know. You never know. And usability is a very interesting thing. It's kind of difficult to predict. You have to literally try things. You literally have to try things. Sort of like a research experiment. 3 + 2 fit. Okay. So and 3. So what fit in there? Some. Okay. So we keep fitting some. It would be kind of, okay, so it would be kind of cool if fit was one of the rules, right? So it would just apply the first one that fits. So I'm starting to have a lot of interesting ideas, but I'll need to think how all of that is ergonomic and stuff like that. Right, so what fits? Okay, some. We're gonna keep applying it until it fits. Right, so what fits in there? Only some ID. Right, we can always see what exactly fits in there. Yeah, as you can see, only this thing fits in there. Right, and because of that, we're gonna just apply it, and there we go. So, and because of that, we may want to actually define this thing as 5. Right, this is 5. Nothing really fits in here, but if you try to fit in reverse, you would notice that 5 is one of the things that fit. Actually, a lot of things fit in here. For example, if you apply 3 in reverse, right, so it just applies it like that. You can undo, of course, that. Right, but there we go. So we managed to prove that. So that's pretty cool. So one of the properties that we probably want to prove is some ID commutative, right, which means that a + 0 is equal to 0. It's kind of similar to the original one, but it's the other way around, right? So that's the original one, this is the other way around, and you can prove this thing by using induction. And I just want to see how well all these new features work in case of the induction. But to be fair, this thing is too simple for this kind of stuff, so I'm not really sure how I want to go about that. We need something more complex, I think. We need something more complex, maybe square of the sum, right? So maybe something like square of the sum. So let's go to the standard library and basically comment out square of the sum, All right, so we can prove it yet again ourselves and just see what's going on in here. Right, so let's actually do RL wrap. Let's load the standard library. Let's do square of sum. Right, so this is going to be a plus something. What? Just a second, 56. So, it's using old style. Okay, so I have a old extension for Emacs for this entire thing. Now it works, okay. Square of sum. So it's going to be a plus b square. Okay, so what fits in here? Actually square fits in here, right? So we can just apply square. All right, so what fits in here? Some commutativity, right? So some commutativity is rather interesting. We can take a look at all of the matches, and that is true. So you can swap this thing or you can swap this thing, right? But the one we're interested in is mul-sum distribution, right? So I'm going to apply this thing here. So what else fits in here? A lot of things, but specifically we probably want to swap around, you know, multiplication. So we want to apply it to all of them. So what else fits in here? Yeah, so we want to do distribution like that. So to all of them. Okay, so what fits in here? Interestingly, if we try to inverse whatever fits, we'll notice that square actually fits, inverse of the square. So we can just do something like this. And yeah, there we go. So, and this is where the ability to specify specific matches is gonna be very useful, right? Because essentially I want to swap this one around. I know that it's a multiplication commutativity, but like which index should I apply? It's the first one. Okay, so that's very easy. So, and I applied the first one. So now I need to apply, you know, some associativity, right? But I have to be really careful, right? So which one can I apply? Okay, so I can only apply the first one, so that's fine. And now, if I try to look at the matches, there's no matches, but if I try to apply it in the reverse, okay, so this is the only thing I can do. So I want to apply only to this one, right? So that means this is going to be the first one, okay. Oh, and here, so whatever fits in reverse, double fits in reverse. I can do double like this, and there we go, so I kind of proved it. It's relatively, you know, convenient, right? So, yeah, it's kind of cool that you can see what things fit in here. So there's no shaping in place, and then you can see what kind of sub-expression match this thing, and you can like exactly pick. It makes it a little bit easier to work with. So isn't that cool? Isn't that cool? So yeah. So we now have two useful features that will allow us to explore things a little bit easier. Right. I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session with Azuzin. I love you all. Mwah!